This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
The numbers are dropping. So some have just arrived for the day, I see. This morning. Oh. Yeah. How's it all going?
Because almost at the end of the semester.
Yeah, we're exhausted, aren't we? We're all exhausted, aren't we?
Yeah.
I certainly am. Are we expecting anyone else to arrive? No? Yes, I need to talk about what might happen next week. Igor and Jack. Is Jack here? No? No, Jack. They were looking for a room for a session next week.
I think they both
A lecture theatre. Do you know which one it was? Okay. I'm sure we'll find out tomorrow then. I hope we will. Okay, so covering off some topics today that we didn't get through. They're kind of like miscellaneous things that we just need to touch on. So we won't strain over this too much. And once again, you've seen probably a lot of this before anyway, so you'll have some background on this from a practical point of view. And it's possible that you've covered off a lot of material already. I'm borrowing fairly extensively from John Webster for the presentation material here, and also our friend Nikish Thakur from Johns Hopkins University. So there's that background. Now we're just going to talk a bit about electrodes, having discussed biopotentials again this morning. It's always been in the background of what we've been doing all the way along here, and we spent a lot of time on instrumentation, basically because I felt that's where the focus was needed for you guys. So now we'll kind of, in these last couple of sessions, including next week, close the loop and wrap it up if we can. A bit similar to the background to generation of biopotentials. The idea of electrodes is where we pick up those biopotentials from, and of course you realise that that involves attachment to the human body, or perhaps a in vitro bench sample or something like that, but basically it's electrochemistry, and I'm sure you guys are as well, probably better off in that domain than I am, being a practicing electronics engineer. I haven't messed with solutions on the bench for a long time, as I mentioned this morning, so you guys will probably have a feel for how electrode materials work in electrolytes, and here's the standard issue of a current flow being progressed from an electrode to an electrolyte and probably back again, with common electrode materials being platinum, carbon, silver and gold. And typically the electrode metal is involved with it's one of its salts in electrolyte, and the typical one that we keep coming back to is silver chloride, because that's the essence of the typical electrode that we deal with. The ones that you've had in the labs last year, we haven't done anything with them this year, but you know the type that I mean. We'll come to it shortly. So a little bit of heavy duty background from Thacker on oxidation reduction that occurs between electrode and electrolyte and back again. These are reciprocal chemical processes typically, and you're already familiar with those from previously, so we won't labour the point on that, but essentially oxidation is loss of electrons and reduction is the gain of electrons through the pathway in electrolyte interface. Now, one of the things that we do have to deal with from a practical point of view with real electrodes is the half cell potential, and that is why specifically the silver chloride electrodes that we've used in the labs here are particularly favoured, because as well as being stable, they have a very reasonable half cell potential, 0.3 of a volt roughly. So that's quite useful for us. And once again, the manifesto is here. Charge separation causes this oxidation and reduction at the interface, leading to a double charge layer, a little bit like the membrane potentials that we saw this morning with the biopotentials. Okay, now the classical electrochemical experiment is with half cell potential measurement with a platinum electrode and another electrode material with measurement in between, and you can see bubbling away there, there's hydrogen being involved at the other electrode. This is the typical experiment, and it's a way of visualising what might happen here. So getting down to tin tacks, these are a bunch of electrode materials that are provided principally by Webster in his text. You can look it up there. Electrolyte pairs here, and once again the one of choice here is the silver chloride electrode. Quite a low electrolyte, potential that we achieve for that half cell. Now, I'm not sure if I mentioned to you before, but when I was a student, my third year project was to make a device to stimulate, and for that galvanic skin impedance device, I cleverly used lead, and I made my own electrode with it. Just got a little bit of bendable lead and cut that and soldered it, because it soldered quite nicely. Solder being lead tin, so I thought I was pretty good with that, until someone told me that I was running a risk of lead poisoning. I only used it on myself, of course, until later one of my lecturers wanted to try it out, so what could I do but let him do it? He chose to. anyway, it turns out that I had harboured that guilt for some decades before I spoke to a neurologist, maybe about 5 years ago, maybe 10. And he said, no, that's fine, lead's okay, as long as it's not at all corrupted, it'll be okay to use. Having said that, I'm not so sure about it, so I wouldn't try it at home yet, kids. It's not a very wise idea. However, can you see why I was attracted to that at the time? Yeah, very low half-cell potential. And notice it's negative rather than positive. That's curious, and I'm not quite sure whether it has a great deal of significance, but bear in mind that when we use these electrodes, there's that little offset potential that will maybe give us some trouble. When you're putting it through an instrumentation amplifier, remember that the DC potential is going to get amplified as well as any signal potential. So if you've got a high gain amplifier, then maybe a gain of 100 or something like that in the front end, that is going to try and amplify to 22.2 volts. And you might say to me, well, okay, it's a differential amplifier, so if we've got 2.2 volts on the other electrode, won't it cancel out? And the answer is, well, yes, but whereabouts does it get cancelled out? It might be outside the operating range of the instrumentation amplifier to do that subtraction with that small voltage present being amplified internally before it's subtracted. So we need to take care with that. Having said that, we're a whole lot better off than we would be with a straight silver electrode, would you agree? Or in fact, a gold electrode. Okay? Yep. So a lot of these materials here are favourable in terms of their, well, I've covered the toxicity aspect, not very well, but it's something to bear in mind. The so-called noble metals are fairly less troublesome as far as the toxicity point of view goes, but be careful to check for that. Copper is another one here that's sort of in range, but once again there's a heavy payload of DC offset with those electrodes. Any questions so far? You? Okay, classification is for perfectly polarizable electrodes and perfectly non-polarizable electrodes. Well, none of them are perfectly one way or the other. We'll pass over that and continue with the silver-silver chloride electrode because that's the one that's of most interest to us at the moment, a good workhorse. And you know what they're like. You've seen them. They look like this, the little clip-on ones, clinical clips or useful alligator clips that you can put onto this button type. You've seen them before. You know how they go. Adhesive layer. The button type, we can just press fit the external snap to it and away we go. There's a gel sponge inside to bring the ion current through to the electrode interface, which is internal here, and that also provides some rigidity to the assembly as well to stop it from wobbling sideways. By the way, these ones that we typically use, the red dots and so on, we call them, they typically last for a day in clinical situations, but then we need to discard them. They are discardable, disposable, and usually easily removed if we're not too hairy on the site. another rendition this time from Webster. I mean, it's the same thing really, no more information on that one. Okay, what I wanted to talk to you about was you thought you were getting away from Bode plots. However, they are useful not only for voltage transfer functions, but here we've got an impedance transfer function in terms of frequency on a log scale versus a log scale, damn it. And you thought you were getting away from it. What this is meant to show is at low frequencies, the resistance is quite high when this shunt capacitance or shunt across the interface resistance is acting as basically a short circuit. Sorry, that'll be up here. When it's at low frequencies, it'll act as an open circuit. Then we'll have RD in series with RS. So RS is of course the inevitable lead wire resistance, and RD and CD are the activity due to the electrolyte interface. So the charge behaviour has a resistive element to it and a capacitive element as well, depending on the frequency. Once again, we look a little bit more closely at the guts of the interface here, showing the various capacitive components, insulating type material with notional plates to it. That's in essence then a capacitor, but there will be leakage across it. So there's the RD leakage component around it. Mostly we'd expect the capacitive element to be in charge of charge carrying behaviour. The gel is here to provide some conformal contact with the skin surface, and there are various layers of skin till we get down to the internals of the activity that we're looking for, which is where the site of the origin of the biopotentials. Welcome everybody. So, in essence, what we can do is we can model all this in conjunction with our model of the amplifier that we're using to deal with the biopotential, and in fact the biopotential itself, the biopotential in question, whatever it might be, an ECG, an EEG, or an EMG. Those can all be modelled and analysed on a mathematical basis if we can get a good model for the electrode and its interface to the skin. So here's some values put on those particular layers, and this is from Joe Carr, and John Brown is the significant owner of Burr Brown Company. In the electrode, with this particular electrode is favoured to have 10 microfarads of capacitance, and that seems to me to be quite a lot for a small red dot electrode, but we'll go with it. 10K is a sensible shunt resistance to observe there. The half cell potential, as we've said before, is going to be about between 0.2 and 0.3 volts for the silver chloride electrodes, and we'll have in the order of tens or hundreds of ohms for the skin resistance and the lead resistance. Okay, I haven't put the citation here for this one, but it's actually Feinberg, Applied Clinical Engineering, and he's given us a little bit more of a feel for what the skin resistances might be in a typical situation of a clinical application in conjunction with the body's resistance itself. So I'm hopeful that at this stage you would feel confident that you could analyse such a circuit and in terms of its frequency performance. And I'm hopeful that you can see that how that fits in with this diagram here. Okay? So can I ask you then, could you patch together those two slides here, this one and that one? I think you've got access to it on LMS. So if you could put those values in and see how well that conforms with this frequency response curve. For example, what would the corner frequency be here for the CD and RD values that are suggested by both Carr and Brown and Feinberg? You with me? Can you plug in these values to see if you can obtain a corner frequency that's consistent with this diagram? Now, what you might need to do is consider what the short circuit resistance is that capacitance CD actually experiences. Okay, or both of those capacitances CD. Can you develop up a parallel circuit for that? Yep.
Just with the next slide.
The next slide?
Yeah.
This one?
Yeah.
Yep.
Where are the inputs and outputs?
The inputs are actually going to be over here. Yeah. It's not shown. What we're really doing here is we've got a dead circuit where the voltage sources that would normally be sitting in here have been regarded as short circuits for the sake of figuring out what the time constant would be. Good question. So here we see that there's the voltage here, not shown as a voltage generator, but because it's in series, we'll assume it is, yeah? And this is, you know, the typical order of tens or hundreds of millivolts. Yeah? Or if EEG, then call that microvolts.
I realise the question's not 100% well posed here, but this is the sort of thing that sometimes you come up against where information, particularly in this arena, is hard to get. When I was a student, I found this particularly hard to find, this sort of information. So you might need to tease it out a little bit. And you do that by asking questions. And here I am. If you feel better about
Working out a voltage transfer function, then you can put a little voltage source in here if you like. And at this point, just somewhere in here.
see if it's consistent, or sorry, see how consistent it is.
With the previous slide,
Up to, yeah.
the only
Yep.
would the only frequency components be just the resistor and the capacitor?
Ah, yeah.
It's in parallel.
Yep. But there will be the effect of the other resistors, which you can imagine in parallel. Right? Can you find a time constant for the dead circuit, is the question. Do you understand what I mean by that?
So,
What, in other words, what, from day one this year, we were looking at what resistance does this capacitor experience? Yeah, what shunt resistance? It's not just R1A here, it's R1A in parallel with RS here, RSA, RT, RSB. Oh, hang on, that's in parallel with the other capacitor, right? So we've effectively got two capacitors separated by a couple of resistances, separated by a couple of resistances. So why don't we think of these DC sources now? They're off the scale, aren't they? Oops. In terms of this here, they're way off the scale. They're way over to minus infinity frequency-wise. So we can regard those voltage sources as short circuits, not worry about their DC behaviour, because in reality we expect these two guys to cancel each other out for the most part. Yep. The practical reality is that they don't in practice. So this is one of the humbugs, is that these offsets are going to be different. The little DC offset will be different over time, and they'll drift. That difference will drift. This is what causes a lot of humbug. But for a first approximation, let's just kill these guys by regarding them as short circuits and see what equivalent circuit you can get from that. And then I'll give you a hint. One thing you can do is imagine that since you'll have a loop with two RC networks in it, and the loop is connected by a couple of R's. Here's one that turns out to be a big value of R, and this one's a small value of R, but they're in series with each other in effect. You can put them together as one resistance in a big loop. Can you see that?
so you said all those paths that are in series
This one and that one.
are in RSB.
You can regard RT and Rin as in series with each other. We can put those guys together because they're in the big loop. However, we've got this RC over here as separate. Yeah. And you might put RC in series with Rin then. It's just a question of whether RC is going to be greater than RT, and that'll depend on what happens over here. But either way, you can regard this as a single resistance, whether this is the big part or that's the big part. They'll both be in series in effect with Rin. Yes? Good. Thanks for the question.
Okay. It looks like a few people are engaging with this, so maybe we'll leave it with you, and I can pick it up tomorrow at the workshops if you want. Yeah. And we'll have a good crack at it once you've had a chance to really absorb it. Okay? Sorry? Do it now. There's a bit of content to get through still, and it's probably good if you have, unless you've got specific questions, we can leave it to engage with on a group basis, yeah?
Like, are we trying to find the equivalence resistance from
Yeah.
one end to
The name of the game is to try and find a time constant that typifies this circuit, right? So, and with that, a capacitance will experience an equivalent resistance. And we know that this capacitor, for example, is going to experience something less than 10 k ohms, because it's already got 10 k ohms in parallel with it. So all this other junk, all the other resistances that sit around it, effectively we can see that they're kind of in parallel, except they're kind of in parallel with this capacitor too. So those resistances in parallel will form an equivalent resistor for that capacitor, defining therefore a time constant, and the reciprocal of that time constant will define the break frequency. Yes? Good? So even with, dare I say, a relatively simple circuit here, it takes a little bit of unravelling. Yep. I'm hopeful you can do that. If you're not confused, you must be mistaken, because it is confusing. Yeah. Sorry? Okay, the output is over here on this resistor Rin. See, it's got the amplifier R. Doesn't show up here, but amplifier input resistance might be a bit of a giveaway there. Yeah. Yep. Yep. That's why I say you get these bits and pieces from different authors who have their different way of expressing things with different symbols. The bulk tissue resistance is RT, yeah. Now you might ask, as I do, the validity of having this in parallel with that. That's a good question. Yep. Worthy of further investigation. Suffice it to say that we can model what goes in from the cell as being a voltage divider driving into some impedance. And as is done here, the input impedance is the driving voltage is considered to be a short circuit. We're just looking at here the dead circuit, that is to say with voltage sources short circuited and current sources open circuited. So that helps us to determine any time constants, which will, once we know those time constants, or that particular time constant, that will, the reciprocal of that will tell us what the break frequency is. Good? So we can characterise the impedance behaviour with frequency. And the takeaway point here is that for this particular scenario, the impedance is is high at low frequencies and drops down at higher frequencies. So bandwidth limited at the electrode. Okay, can we move on for a bit? Who wanted to keep at it right now? Who was that? Oh, all right, then we can do that. We'll push on with it then. Throw away the scripts. Yep. Sorry? Sounds plausible. I haven't actually worked it out. We can work it out together. Yeah. So, okay, how would we analyse this particular circuit? What do you think?
Start by cleaning all the outside resistors, like you said.
Group them together?
Yeah.
Yep. So we've got 2.1k there and 2 megs on this side. Yep. Should we spread it out? I won't do it on the board because the viewers at home won't be happy with that. Okay, I've consolidated as much of that now, so I can swap over to the document camera now. If this thing works. Okay, so let's consolidate. Is that going to stay in focus for us? All right, so we're forgetting about these, aren't we? Yep, we're just regarding them as short circuits. Yep. So let's redraw if we can, shall we? We'll put the two capacitors as the subjects. This is I'm putting the lower one first. And I should really refer to them as C1 and C2. That might make it easier, mightn't it? Is that reasonable enough? What have I missed out? The 1K resistors. Yeah. Well, that's fairly easy. I'll just make this 2.1 k ohms. 2100. Good.
I've sorted that one out. All right then. So we can then port the 2 megohm resistor in series with those guys, can't we? Yeah? That's a big resistor now, isn't it? Good. Now what do I do?
Could you combine capacitors in parallel?
How can we do that? Because they're not exactly in parallel, they're branched by a 2 megohm resistor. Maybe we can just see what happens with each capacitor by itself. Yeah. Let's forget that capacitor for the moment and say we've got 10k effectively in parallel with this series connection, which is looking to be pretty large resistance compared to 10k. Yeah. So maybe after all this huffing and puffing, we just come down to 2 isolated RC circuits. Yeah. The very worst that can happen, if this capacitor is acting as a complete short circuit at very high frequencies, it'll seem like this point is connected to ground. If we regard the capacitor as open circuit, then it's got this resistor in series with it. So we're either having 2 megohms in parallel with this 10k, or 2 megohms plus 10k ohms. Either way, it's not a big deal. Just it'll modify things just a little bit. So ultimately, at the end of the day, I'm sorry this is hunting around a bit. It's better to put something there to focus on. So all we really need to do is figure out the time constant of these 2 components, which is 10 to the 4th by 10 to the minus 5. Am I right? Mm-hmm. Yes? So 10 to the minus 1. Okay, now that then would define a break frequency which is omega equals to 1 on torr, which would be 10 radians. In other words, I'll put it sub C, the frequency will be 10 divided by 2 pi. 1.6 indeed, hertz. Okay, so let's have a look at what we have back here, and it's a little worrisome because it's nothing like that at all. It's 100 hertz where that break point is. Yeah, 100 hertz. And it looks like awfully like it wants to be 160 hertz, doesn't it? So are we a couple of thousands of 10 out somewhere? What do you think?
Well, there's no reason in the world why the form of this circuit needs to match the circuit that we have from previously. The values are just ambit values. So whilst this predicts the form, it might not predict the actual values. It might apply to very much smaller electrode size. And we probably have to chase up and see what Webster's ideas were for that when he proposed this one. But at least we see the form of the circuit and we can understand how it might work that way now. Yeah? And we'll follow through on that with a bit more detail. Need more light, I think. So what I'm saying is, the values that I gave to you would predict for the ones that these two other authors have proposed for us. They haven't told us what their frequency response is, but we would say that this is a typical clinical electrode. It looks like it would work quite well down at very low frequencies, wouldn't it? Whereas this one here is a more tailor-made one to perhaps higher frequencies. Okay? Some work to follow through. Okay, we've got a few more minutes before the notional mid-break. What I did want to talk to you a little bit about was the heavy-duty information overload that we've got here, talking about motion artifact, which is one of the things that bedevils us. And like I said before, that's largely due to movement between the skin and the electrode, or the electrode foam layer within its housing, that will create a change in impedance in the pathway. So the various methods to deal with that are stronger encapsulations, like we have here, for example, to hold things a bit rigid, and the sorts of suction electrodes that you might have seen. I might have some images, I think I've got some images here further on, or flexible electrodes and other ones here. So these are very arcane looking old things that we still see used from time to time. Solid electrodes that don't have the foam pads that we've just been talking about. They are occasionally in use and they do have their applications. And the suction type of fixing arrangement, just with a bulb that you squeeze, put it on, let the bulb go, and it holds itself on. Often used for chest electrodes, as mentioned here. Same story here, roughly, with the silver chloride disc electrodes. Other ones that are used are the round rubberish type ones that we see used for conformal body surfaces, and useful in pediatric cases and so on. Okay, so when we get to doing EEG electrodes, then quite often gold type electrodes are used, tend to be a lot smaller and more easily affixed as scalp electrodes to get around the, as you appreciate, EEG signals are several orders of magnitude lower than EEG or EMG signals, so to get around the volume conduction problem from where the action is of the signal to the surface, as we encounter more resistance. So quite often it's appropriate to take the scalp, remove the top of the skull and put in electrodes directly on the surface of the brain. And here's a group of electrodes placed like that. Sorry, I meant to say that there are typical montages, as we call them, for putting
electrodes in specific sites as much as possible for surface electrodes. This is a fairly old depiction, so quite commonly there are vastly more electrodes these days for surface electrodes. As I said, if we need to get larger signal and removal of the skull and direct mounting to the to the brain itself. The sorts of things that need to be done for EMG studies sometimes involve electrodes that go within muscle, typically, and so needle or wire electrodes are used for that, and you'll appreciate that there are some quite straightforward arrangements that are not without their issues. And here's the case of electrodes for babies in utero still, with electrodes attached while they're still internal. And then we have the electrode arrays for measurements from the brain, sometimes rammed in fairly heartily with fairly abrupt insertion techniques and regular grid arrays. The Utah array is one of those, for example. Microelectrodes are often for doing direct cell measurements, and there are quite a zoo of these devices, metal, glass and so on. We don't really have time to discuss them here today. What we need to talk about a little bit, and I was going to do that in the second hour, is to move on from the microelectrodes and so on to talk about stimulating electrodes, and I'll come back to that after we have a bit of a break. I think we're due for a break now, so we'll come back and talk a bit about those more clinical device electrodes that are encountered in clinical practice. So, questions before we break? Igor, you got some good news for us for next Friday, have you? Or? Okay, you'll let us all know about that. I take it I'm invited, is that right? Okay, can I buy a ticket for that? Okay, well thank you. Okay, we'll resume in a few minutes then. 20 past? We'll resume at 20 past 4. Yep. Press here to pause.
Maybe I'll log
Someone's charging up. So you're charging down here because it's charged up. That's all right. Got enough? Got enough ergs? Let's resume then, if we may. I did. So I'll push it again, that'll turn it off. It says recording. Hello? I wanted to talk about, in the context of electrodes and stimulating electrodes, one thing that's of interest is, well, there are two actual heavy-duty clinical apparatuses that might be covered in the subject clinical engineering in this course, I'm not sure. Has anybody done the clinical engineering unit subject? Okay.
It's probably not going to run next year, next semester, because it's not an option on the study plan.
Oh, okay.
Yeah, it was meant to be semester 2 something, but I've looked at like the last 2 weeks, like a couple weeks ago, and it wasn't there as an option to select it.
It's a shame because it's a great subject. Sounds like a great subject.
Might be able to organise something, I don't know. Bear in mind that I'm available if you want. Okay, traditional surgery with a scalpel has got some issues with it. So we separate tissue mechanically, and there's a lot of pressure on the blade because the actual cutting surface area is quite small, if you'll appreciate. So the philosophy is there that you rupture the tissue to form a cut. However, electrosurgery, sometimes called diathermy, in that instance we use RF power into a pencil-type blade that actually boils the tissue, and that provides the separation, the cut. So, how does it work? Well, it's a high-frequency generator, and it's a return path through a second electrode that's typically on the buttocks or the back or something like that. And that forms a return path so that the exit for the current is spread over a wide area. Whereas at the cutting edge itself is like a pen at a point. Charge concentration is very high. So the advantage of that is you get hemostasis, cauterization at the cut itself, so that deals with bleeding to some extent. Okay, here's a fairly old. Yep.
Just with that, would the line of cutting be as straight as a normal scalpel, or would it
It sparks a little bit, yeah. So the line can be as good as the surgeon's hand is. Yeah. All right. This is an old style ESU, electrosurgical unit. Valley Lab now is owned by Covidien, which is owned by Medtronic, and truth be known, most of us in the world really work for Medtronic, but we don't know because they own everything. No, I'm being facetious here. It's probably General Electric who owns most of the world, but things are getting corporatised and there's been a lot of acquisitions. Valley Lab is now owned by Medtronic, and Valley Lab are one of the major players in electrosurgical equipment. The reason why I put this up here is to show their suite of devices, and these are the cutting stencils here. So there's you can appreciate it's like a fine, very fine tip scalpel stylus arrangement, and some bipolar ones where the cut is between 2 points. What I really wanted to show you is the return electrodes, and I wanted to bring some along today, but I've just been rushed off my feet and I didn't unearth the ones that I have at home to bring to show you. But they're, you know, pads JD. So if you can imagine, this is on one side of the patient and the cutting's on the other side, so the current density is spread over an area collected by this return plate. So that's one of the things that makes it easy to use this technique to perform surgery. Here's a couple of waveforms that are used. So this is pure sine wave and fairly high voltage for certain applications and to coagulate. To coagulate the damped sinusoid is often used, or you can have a mixture of it for different applications. It's a so-called blend mixture. All right, what I wanted to talk to you about was that here, why can we do that? Well, it turns out the dangerous aspect is at generally lower frequencies. As chance would have it, the worst possible frequency for electric shock is mains frequency that we have here or in the USA. So around 50 to 60 hertz, it's the worst possible frequency to apply to yourself from an electric shock point of view. The fact that these things are operated at very, very high frequencies, we don't get the dangerous current levels quite as readily at high frequencies. So there's a lot of value in running at high frequencies. You don't get the usual electric shock or macro shock or micro shock occurring. Here's a depiction, if you will, of the cutting being done with that stencil at a point, and you can see that the return path is spread over the area for the return pad. So this is an example of an electrode that's used at high power, and the major issue with electrosurgery is making sure that that return electrode is across a reasonably wide surface and it's not folded or bent or otherwise unserviceable, because that's what causes the majority of the problems. But if I had been able to show you this thing, it would have been a lot easier to give you a feel for it. Quite a large electrode. The ones we've been talking about earlier on, as you know, are very quite small ones for recording, but this is a return path for stimulation. Oh, I had a question, but this is a sample question, but I didn't evolve that properly, but you can have a look at it anyway. It's a typical, shows typical values, an amp or so at half a megahertz, and the test is typically 300 ohms. That's possibly a little bit over, above what's done in normal body scenarios, but it's a test value that's used. Okay, the other application that I wanted to talk to you about is defibrillators, and we didn't get very far into the discussion on, cardiac aspects, and that's principally because I thought that stuff gets covered over in clinical engineering. So the reason why I've been steering clear of this applied equipment stuff is simply because I thought it was the province of the clinical engineering subject. Now I find out it's not running, just in the nick of time. Can't do much about that. Anyway,
Still in the handbook
it is.
as being run by David Braden. I don't know if that's changed.
Okay, we can talk to David if you like. Okay. Yes, defibrillators are really meant to provide a largish shock. It depends on whether it's an indwelling defibrillator or an external defibrillator, and you've seen them on being used on the TV shows, ER and so on. Chicago Hope, and they always turn. The reason why you would know what the largest value that you can get from a defibrillator is on those TV shows. They always wind it up to the maximum, which is, oh, you don't watch TV enough, you guys. 360 joules. They always seem to go for the maximum, which is a bit crazy because it's hardly ever clinically indicated, but there you go. Can you see these electrodes here, fairly big ones, large paddles sort of things, obviously placed on the chest, and you can see the sighting of it there. This is the one that you get talked through, what do they call them, AEDs now, don't they? And you can find them around the university and in certain supermarkets. So those ones give you instructions on exactly where to place, and they do the test internally to make sure you've got it in the right position and so on. And in doing that test, they will tell you whether you've got the electrode placed correctly, because it runs a small test current through to check to make sure you've got it in the right spot and everything's lined up with the appropriate amount of resistance. And talks you through exactly how to run these things. Has anybody done a first aid course where you've had training with these things? That's good. I'll know who to fall down in front of. Yeah. Okay. So here's the traditional sort of defibrillator, the old style one. And what that involved was charging up a capacitor here. Yeah. And when it's switched in, it's a CLR circuit. Somewhat like that circuit that you would have encountered for the filter section that we did earlier on. Do you remember that one? I think the capacitor was on the other end there. But the idea is that the capacitor will dump its discharge through the patient. The rationale for having the inductor present there is to make a damped circuit with a little bit of oscillation to it, but not much. And the whole idea about that is to dump the energy as quickly as is needed, but not too quickly, so that we don't end up re-stimulating within the vulnerable period where the cardiac cycle has resumed. That's a little bit complicated to explain since we haven't gone into it, but you don't want to restart the heart at the wrong part of its cycle. So, in terms of the decay relationship here, the the waveform needs to be strategically organised to decay at the right rate that we call critically damped. So if it were underdamped, then we would see an ongoing ringing. Yeah, we'd see a sine wave that had an exponential envelope on it. If it were overdamped, then it would converge to zero at a slower rate. This is really meant to go just under and flatten out in optimum time. So it's strategically organised for a couple of appropriate resistance values, and there'll be a big inductor in this old style of machine. This is the older machine that I grew up with working on the bench, and the main thing was that it had to have bulky batteries to it. Oops, sorry about that. And we used to have to test them once a week to make sure they were working. What that did was it meant that we just run the thing down. So in order to test it, we had to bleed energy off the battery. Okay, so there's a logistical problem with that. How do you make sure a defibrillator's got enough charge to it? The only way to do that is to have two batteries, one that's perpetually on charge and the other one that's being deliberately discharged, because there are certain batteries that need to be cycled in order to work. That means the weight doubles, which means its usefulness as a crash cart type scenario is difficult. So there are logistics problems with whatever you do in this arrangement. Couple that with the nurses who would always have these things plugged in and have NiCads overcharged, thereby wearing down their lifetime. It was very difficult to manage. So that's where you need engineers to strategise how to deal with these particular systematic problems. Okay, so that was the old style, as I said. These days, the wave shape is organised to be more trapezoidal by some more sophisticated electronics. These are not transistors, so don't get too scared. They're worse than transistors to understand. So yeah, silicon controlled rectifiers. They look like diodes, and they are sort of diodes, but they're complicated devices. So just accept that there are timing circuits here to gate these things to provide that arbitration of charge dumping into a patient or a subject as quickly as possible. So that's what I have for you today as a rundown on electrodes that you would encounter. Is it? Questions? I did have a sample question for this, but I didn't. I wasn't sure whether you'd accept it very well. I'll put it on LMS for you. Any questions? All good? Everyone's happy? Got people coming to the workshops tomorrow? Yes? Who's finished? 1, 2, 3. Well done. Who's coming? Who's yet to finish up? All right. So, I'll call it quits there, and we'll have a